Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list published on July 20th, 2025, so about 5 days ago. This paper presents a new method that reduces computation by over 50% on average, while at the same time improving accuracy by up to 3.37%. The paper is titled MUR, Momentum Uncertainty Guided Reasoning for Large Language Models, and it manages this without any extra model training, which is quite a clever approach. Essentially, it uses an idea from physics to help models avoid overthinking and focus compute only on the most critical reasoning steps. Also worth noting, the project code is available on GitHub for anyone who wants to explore it further. On the Hugging Face page, you'll find the official code for the MUR reasoning algorithm with usage examples, but it doesn't host any model weights for download. Alright, so the first figure here really sets the stage. It compares 3 different reasoning approaches. The baseline is a standard method called chain of thought, which just thinks step by step. Now, moving from that baseline, you see the per step scale method. This one improves accuracy, but it does so by throwing a huge amount of extra computation, or tokens, at every single step. But then you have MUR, the new method. It achieves comparable, or even slightly better, accuracy. And it does this while using dramatically fewer tokens, cutting the computational cost by more than half compared to that brute force per step scale approach. This chart really visualizes that core idea of working smarter, not just harder. Building on that, this next figure gives us a more detailed look at how these methods actually work. You see the standard chain of thought, just a simple linear process. Below that is the per step scale method, which applies extra computation at every single step. Very inefficient. Then we have MUR. It introduces a concept called momentum uncertainty. At each step, it calculates the model's immediate or step level uncertainty. This is then used to update the overall momentum uncertainty, which is like a running average of the model's confidence that smooths out brief fluctuations. This momentum uncertainty then decides when to trigger a scaled step, adding compute only when the model seems genuinely stuck, like at step 2 here. This selective scaling is the key. Okay, so this table lays out the main results, and it's quite impressive. The authors test MUR against other approaches across 4 challenging benchmarks. Now, these other methods are all types of test time scaling, which are techniques that improve reasoning by adding more compute during inference. The table shows accuracy, measured as a pass at 1 rate, which just means the model got the right answer on its first try. You can see MUR consistently achieves higher accuracy, while dramatically cutting the token count, often by over 50%. This strong performance really validates using momentum uncertainty to guide computation. Moving on, these plots dig into a really neat feature called gamma control. Now, gamma is a hyperparameter, which is just a fancy term for a knob you can tune to adjust the model's behavior. The charts show that as you increase this gamma value, both accuracy and the number of tokens used also go up. What's crucial here is that you can use gamma to find a sweet spot, achieving accuracy that's better than the old per step scale method, but with a much smaller computational budget. This ability to tune the trade-off makes the whole approach really flexible. And here we see a fantastic case study that really brings this all together. It shows a side-by-side comparison of MUR and the per-step scale method on a difficult math problem. On the right, the per-step scale approach thinks hard at every single step, but all that extra unfocused work actually leads it to the wrong answer. Now on the left, you see MUR. It only triggers deeper thinking when it detects high uncertainty, and this selective, targeted approach not only saves compute, but also guides the model to the correct final solution. So to wrap things up, the big takeaway here is that MUR, or Momentum Uncertainty Guided Reasoning, offers a very elegant training-free solution to the overthinking problem in LLMs. It uses a core idea called momentum uncertainty, which is a running average of the model's confidence, to intelligently guide test time scaling. These are methods that add compute to improve reasoning. This targeted approach leads to the best of both worlds, a massive 50% plus cut in computational cost and better accuracy. That's all for this roundup. Thanks for tuning in.